opportunity to introduce the next speaker. So Zihao Shu, or David, was born and raised in Xi'an, China. He still distinctly remembers his first math class, linear algebra, with Professor Sarkis, and that he forgot to draw the eigencat as part of the final exam instructions, which cost him 2 points. Poor David. From then on, he carefully reads all the exam instructions and advises his friends to do so as well. During the summer of his sophomore year, Zihao had the honor to work with Dr. Hardin on a research project in machine learning. Subsequently, he also took one of his favorite classes, computational statistics, with Dr. Hardin, and decided to become a math major after that. Looking back at his 4 years in college, Zihao is immensely grateful for his education at the math department, and today he would like to dedicate his presentation to his professors, his friends, his girlfriend, and his parents. Present to you, David.
Thank you everyone for your patience. So I'm the third speaker of today. My topic today is going to be on appearance-based eye tracking using convolutional neural networks. So those words might not make any sense to you right now, but I'll go into details. Before I start, I would like to thank my advisor, Professor Palpazaki in the CS department, for her generous support. So to begin with, I would like to introduce the concept of appearance-based eye tracking. So essentially, this process is the mapping between a frame image of a subject's face to an XY coordinate on a computer screen. So to illustrate, you can see that these are two images of two subjects, and what I'm trying to do is to build a model that's able to predict the X and Y coordinates and then map it back onto the screen to see where the subjects are looking at. So why is eye tracking useful? To start with, some online marketers might be interested in gaze coverage, or whether they're interested in user behavioral patterns, so that they can more strategically place their web content or advertisements so as to maximize efficiency or profits. At the same time, assuming that we have a very accurate eye tracker, we can also build like interactive games and some accessibility tools to enable disabled people to interact with laptops and desktops. So just to give you an example, this is a gaze location heat map on a Google page. So as you can see, sometimes people look at the certain spots of the web page more than other places. So since eye tracking is so useful, I would like to explore the current options that are on the market. So the first option I encountered is called head-mounted eye trackers, and it looks something like this. And then after staring at it for 5 seconds, I'm like, maybe not, this is a little bit too much. And the second option that we have is called remote eye trackers, and it looks something like this. So as you can see, that little sidebar called Toby is a professionally dedicated eye tracking tool designed by this company called Toby, which is very accurate after an initial calibration phase. But the problem with this device is that it can cost up to $50,000, and this is just my response to that. So, in light of these problems, in my thesis, what I'm trying to do is to build an eye tracker that satisfies the following conditions. So it has to be accurate, meaning that the predictions will be relatively close to the actual base locations. It should be easy to use, which means that it's free of external constraints such as the headset you have to put on your head. And it should be scalable, which means that it can be easily distributed to a large amount of audience. And finally, I want it to be free for everyone to use. So here are the steps I went through in my thesis. So I started with gathering the data and exploring the data a little bit, and then I used what's called facial landmark detection, which I'll explain later. I went through the image pre-processing steps to feed the images to model, and then I built, evaluated, and compared the model with past model performances, and finally I mapped the prediction back onto the screen. So in the data gathering phase, I obtained my data from the WebGazer project, which also happens to be the PhD dissertation of my thesis advisor, Professor Palpazaki. And it's important to make it's important to say that I use WebGazer as the benchmark, which means that I'll be comparing the performance of my model against her model to see if I can make any improvements at all. And in this data set, we have in total of 45 participants, each using a PC or a Mac to complete a series of studies, including reading, web search, typing, and the 9-point calibration task. And the data itself contains recording of the computer screen while the participants are doing their studies, as well as recording from the webcam of the participants' faces. And at the same time, it's really important to point out that we also have frame-by-frame gaze locations predicted by the Tobii professional eye tracker, which is the very expensive one I showed you earlier in the slides. And because it's very accurate and it's like basically clinically proven that it's very, very accurate, one assumption I'm making here is I treat these predictions as the underground truth. And finally, we also have like some metadata on subjects such as demographics and lighting conditions. And finally, after parsing all of the videos, we get a data set that contains 49,000 frame images marked with Tobii coordinates. So after I gathered data, I want to explore the data set a little bit because I want to make sure that there's no intrinsic bias that's present in the data set. This is very important because as we've been talking on campus, there are a lot of machine learning models that have that exhibit algorithmic bias because of the data set is like very biased in certain ways. So I just want to make sure that this is not present in my data set. And at the same time, I want to explore if there are differences in the Mac versus PC groups. So some exploration of my data shows that the number of participants and number of images are pretty well balanced in terms of gender, so male versus female, and also in terms of device use, PC versus Mac. At the same time, I also explore, because I have access to the demographic information, I also explore the race and vision of subjects. As you can see from the left pie chart, this dataset lacks some racial diversity. But on the right, you can see that this dataset is pretty well balanced between people with normal vision versus those wearing glasses. This fact is pretty important to us because people wearing glasses might be more difficult to be detected through like my facial landmark detection scheme. And the second goal of my exploration phase is to assess whether there are differences between PC and Mac groups. So what you see here is a scatter plot of the gaze locations for the two different groups, with Mac group color in red and PC group color in blue. As you can see, the distribution of the gaze locations for those two groups are pretty different. And this is very important for my model building because if we're just to begin with predicting very different things, it makes sense to have separate models for each of the groups. And then just to put that plot in a normalized space, so as you can see, the distribution of y coordinates and x coordinates for the two groups are also very different. And the differences are especially conspicuous in the y direction. After I explored the dataset, I use a technique called facial landmark detection. So that essentially means that I use an open source software called OpenFace to detect 66 strategic locations on people's faces. So as you can see, this lower figure shows you all the 66 points. And with this, we're able to tell where the eyes, the subject's eyes are and where the boundary of his or her face is. This is a picture of me, again, using this software. As you can see, my face is clearly marked with all those coordinates. So after the facial landmark detection for each of the frame images, I'm now ready to move on to image pre-processing step. So we start from the original frame images. And then we would use, we would extract the eye coordinates from the facial landmarks we just detected. And here I'm especially interested in the eye coordinates because one big assumption I'm making here is the image of the eye of each of the subjects are the most predictive of where they're looking at on the screen. And then I would extract a bounding box surround the left and the right eye and then stitch those two images together And finally, I will perform something called histogram equalization. So histogram equalization is a technique that's used to adjust the intensity of image. So what does that mean? So let's look at this picture on the upper left. So you can see it's a black and white image where all the pixels are kind of like very unclear, squashed together. And mathematically speaking, that's because the intensity of each of the pixels are very much concentrated together. And this is why you couldn't really see any of the details inside this image. And after this histogram equalization step, we can see on the lower left that the contrast of this image is significantly enhanced. And mathematically speaking, the distribution of the intensity of each of the pixels, its CDF follows a linear shape. So this step is very important to us because for some of our images, the lighting condition aren't as good, so we want to use this technique to enhance contrast to see the details. So this is basically an illustration of the 4 steps I took. So we start from the original image, we will mark the facial landmarks, and then we extract the bounding box, and finally use histogram equalization to make the image clear for the model to see. And these are like more sample images. One thing to note that on the lower left here, we have a subject wearing glasses. As you can see, this algorithm also works very well for subjects wearing glasses. Now with all of the data ready, I'm now ready to build my actual model to do the grade prediction. So during my thesis, I was inspired by recent developments in the field of computer vision, which is why I decided to use convolutional neural networks for my model. Because this model is very complicated to explain, in my thesis, I dedicate 2 complete chapters to the explanation of this algorithm. But here, I'm going to spare the audience with the mathematical details. But essentially, CNN is a variation of the standard neural networks. It's able to detect patterns and form higher-level abstractions of images. And it can be applied to classification and regression. So classification basically means you're trying to assign a class to an image, say cats versus dog. And regression means that we're trying to get a numeric prediction from the model, which is our case, Gaze coordinates, because it's x and y are numbers. So this is a graphical illustration of CNN. So during training phase, we would feed a lot of labeled cats and dog images to the CNN model. And then in prediction time, if we feed the CNN with a cat image, CNN is able to detect higher level features of a cat, and then finally give you the prediction of a cat for a cat image. So for my actual implementation, I used the Keras package inside Python, and I experimented with 2 different CNN architectures. The first is called MobileNet, which is very, very lightweight and very fast, and as the name suggests, is used for mobile devices. And the second one is called ResNet, which is designed by Google. It's very deep and very complex, but it's very, very accurate as proven by experimental results. And then, because of the differences I mentioned for the PC and Mac groups, I decided to build different models for 2 groups. And since I'm using 2 different architectures, that results in a total of 4 different models. And finally, one important thing to point out is that I'm using what's called cross-subject validation. That means during training time, I would train the model on this set of subjects. But during testing time, I would test it on a different set of subjects. This is to ensure that the model is able to generalize to future unseen subjects. So after I built my model, I used 2 performance metrics to assess my model performance. And as you can see, the first metric is called mean absolute error, which is the average absolute distance between the predicted value and actual value. And UDist here is simply the average Euclidean distance between the predicted coordinate and actual coordinate. So one important thing to keep in mind is that smaller values are better. So I assessed all of my models, my 4 models, as well as WebGazer in the PC and Mac settings. And I found out that so CNN-based models generally performs a lot better than WebGazer, the WebGazer model, which uses a ridge regression as its underlying algorithm. And another observation is that deep CNN is better than shallow CNN. That's because ResNet is better than MobileNet, as you can see from this chart. And my best model presents a 25% decrease in terms of Euclidean distance in the PC group while a 10% decrease in the back group, which shows that my model performs significantly better than WebGazer. And here's a distribution of the average Euclidean distance for both of the groups. As you can see from this distribution, the CNN model's distribution are significantly closer to 0 than the distribution of WebGazer. And that means my model is performing better than WebGazer. And finally, here comes the most exciting part of this presentation. So I would like to show you an actual working product. So in this video, I'm going to show you an unseen subject. So that means that during training time, my model didn't see any images of the subject. And he's performing a writing task. And then I colored the true value in red, the CNN predictions in green, and WebGazer predictions in blue. And then one last thing to keep in mind is that I use transparency to denote the performance of my predictions. That means when the predictions are very close to the truth value, I will give it more color, versus when it's very far away from the truth value, it basically becomes transparent, you can no longer see it. So whenever you don't see anything, that means the prediction is pretty bad, or the prediction is unavailable. So now, without further ado, I'm gonna show you the video. So that should be good enough to illustrate my point. As you can see, the CNN coordinates predictions are pretty much closely aligned with the true values. But I realized while I was watching this video, I just realized at certain times, the CNN predictions kind of fluctuates up and down, like very wildly. And I was curious what happened at those moments, and like what is happening with the subject at those times. So I just looked into a little bit further I just plotted the y coordinates against the frame number, which you can treat as time. So at certain locations, you just see the sudden jumps of CNN predictions in green. And as a matter of fact, I found out at those times, the subject was blinking. So as a side effect, my model is actually able to detect blinks while the subjects are performing the study. So I'm gonna show you a slower version of the same video of those blink times to see if you can find the correspondence between the blinks and the drops in CNN predictions. If you have discovered those correspondence, good for you. If not, my video is available online, so like you can check it out if you're interested. To put everything into conclusion, in my thesis, I built an eye tracker that is easy to use. It's fairly accurate and scalable, and most importantly, it's at no cost. I just used Professor Papazaki's lab to use free open source software to build the entire thing. Some future directions for my model includes, of course, more data, because the entire study was conducted in a controlled lab environment on a limited number of subjects. So in the future, I would like to feed the model more data to improve its performance. And I can also build a better model by using more inputs, because right now I'm only feeding the model images of the subject's eyes. So we can imagine we can imagine feeding the model, say, the position of the subject's head or the distance between the subject's eyes and the screen. Those information, I imagine, will also contribute to the model performance. And also I can add in time dependency, because right now, as you can see, a common problem with the CNN model and the WebGazer model is that it has a lot of fluctuation, because and that means the previous prediction and the next prediction can vary a lot. Like it can be at two completely different locations. So maybe adding in some time dependency of the predictions on previous predictions can smooth out the predictions a little bit more, so as to better the model performance. So, because I'm a math major, so it's like, and then, thank you.
Do you have any intuition behind why the data for PCs and Macs is so different? And then going off of that, how do you think the difference in that data between what seems to be two similar machines, how do you think that speaks to the ability of this kind of technology to extend to things like phones and other
Right.
more different?
Yeah, that's a great question. So the differences between the PC and Mac distribution is because of, first, the screen size. So the Mac screen size is significantly larger than the Mac's screen size. Sorry, the PC screen size is larger than Mac screen size. And also the position of the two devices are also different. So while the subjects are doing their study, you can imagine this monitor being in front of them versus a laptop that's kind of facing upwards at their face. So I think those two factors explain the differences in terms of gate location. And in terms of like the applicability of my model to mobile devices or other devices, I think this problem, the fact that I'm building two different models for these two different scenarios kind of illustrate the necessity to build like different models for different devices. Because as you can imagine, when the subjects are looking at their cell phones or mobile devices, it's going to be much different than the scenarios presented in my thesis. So I guess one remedy would be to like build a completely new model using its own data, or I can build a humongous amount of data, feed humongous amount of data to one model to make sure that it can generalize to like other scenarios as well.
In the video, it seemed like, I don't know if this is a wrong observation, but it seemed like the CNN predicted value was a lot closer to the truth value towards the center of the screen. So it seems to me that the predictions become accurate when you're really looking at the center of the screen. Have you considered including with the eyes like a pointer for the nose as well? That might be a better predictor for where you're looking on the screen.
Yeah, that's a good question. So the fact that the predictions are like very accurate towards the center is because the model was exposed to a lot of images where the subjects were looking at the middle. So at the same time, it can like it's able to know that when the subjects are looking slightly off the middle, if you give it a middle prediction, like the error is like pretty small compared to if you give it a very extreme prediction, say on the left. So that might be more wrong than if you give a middle prediction. So that's why a lot of times it performs better when the points are in the middle. And sorry, what's your second question?
I was just wondering if you've considered including the nose where.
Oh yeah, so I've actually seen someone building a tool where you can basically use the facial landmarks to act as a cursor to point at certain locations on the screen, and it works remarkably well. So I think that's a very important input I can consider in the future, to just adding all of the facial coordinates. Maybe I can use that to predict the direction of your face, and then in addition to the image of the subject's eyes, will produce a better performance.
Are there any specific places or ways you'd like to see this used in the future?
So right now, I think because this technique has a lot of practical applications, and right now I basically just focused on the academic side of it. I think if this technique were proven to be successful, this is also a wish of Professor Papazaki's. Basically, we want to like democratize this kind of technology to wider use for researchers to like conduct studies on website placement, or like say for psychology studies where people are interested when they're presented a new image or something like that.
Vedant asked a big part of what I was going to ask. But I'm also curious in Professor Papazaki's controlled experiment, like what are the control vectors? Are everyone required to not change their head position, or are they required to stay still? And my question is, so in the future when you want to apply this model to a wide range of human movements, do you think it's technically possible to use the Toby device to actually label that diverse range of movements? And alternatively, what do you think is a possible solution to overcome the labeling problem?
So I guess I'll answer the second question first. So the labeling problem is definitely a huge problem that's like for this data set without the labels created by Toby, I wouldn't be able to make anything, build any model at all. So in the future, I think I don't think this is a completely reliable way of collecting data, just because the user might not have access to such an expensive device, and at the same time, I can't really distribute this to everyone out there. So I think we might need to devise some other kind of data collection techniques. And in terms of the constraints that's on the subjects, so the only constraint was that they were sitting in the lab environment where the background is white, and that's the only constraint. So they're free to move their head wherever they want, which is why my model is pretty robust in the prediction phase.
I mean, just building off of that, I know in econ that they've started using mouse tracking instead of eye tracking, because obviously there's a measurement error component to it. Do you think that could be one possible solution to scaling the problem of labeling?
Yeah, so actually Professor Papazaki's model, WebGazer, uses a very different way to collect their data. So their model has an initial calibration phase where you have to click on certain points, on actually 9 different points on your screen. And at the moment when you're clicking at those points, the webcam will capture one picture of your face. So effectively, you're building up the data set on the fly and then train your WebGazer model and then do prediction. So I think those kind of interactions, such as mouse click, can also be added as part of my model in the future, because one reasonable assumption to make is when the user is typing, his or her eye will be looking at when the words are appearing, and or when he or she is clicking, he or she is also staring at the same point. So I think those will definitely be conducive to model performance as well.
How much data is necessary for your neural net to work well?
This is a very good question. I haven't experimented with, like, say, different data set sizes, but what I do know is that the current size of the data set can give you a pretty good performance.
Let's take any additional questions.